Greetings for the day, everyone. My name is Naveen Jalapur, and I'm excited to present our project, Predicting House Prices Using US Housing Data. This work is a collaboration with my team members, Shivakumar Yadav Vallala and Jayendra Varma Datla. We will show you how machine learning can make accurate house price predictions to help users. Here's the outline of our presentation, which includes the introduction and related work and the type of dataset that we have used and the proposed work and results, and followed by conclusion and future work, and finally the demo of the UI that we have built. Coming to the introduction, there are traditional ways of predicting house prices, like relying on expert opinions or general market trends. They often miss the mark because they can't capture the complex relationship between the features. For example, a house size and age interact in ways that are not obvious. Our project addresses this by using machine learning to make smarter data-driven predictions. So our aim is to build a model that's both accurate and practical for real estate professional and regular users. And now coming to the related work, there are traditional approaches in predicting the prices of a house, such as linear regression. Now, linear regression is one of the earliest and simple models used for predicting the house prices. But linear regression struggles to handle non-linear relationships in housing data, such as exponential rise in prices for properties or the influence of raw features. Linear regression might predict a house with larger lot size to always have a higher price, ignoring the effects of other factors. Coming to the advancements in machine learning brought advancement techniques like decision trees and random forests, which are better at handling complex patterns in data. Decision trees is a simple yet powerful model that splits data into subsets based on feature values, and it is easy to interrupt and visualize, but it is also prone to overfitting. Whereas random forest is an ensemble method that combines multiple decision trees to improve performance. In random forest, each tree is trained on a random subset of the data and features, and the final prediction is the average of all trees. Random forest reduces overfitting by averaging the predictions. Many studies don't provide clear explanation of which features are the most important in determining the house prices. Our project builds on this foundation by addressing these gaps. Whereas feature importance studies lack in transparency about what features impact the model more. And now talking about the dataset. The dataset that we have used is sourced from Kagel's USA housing dataset. They may raise a question that why we are using this dataset. It is because it's comprehensive and covers various factors that influence the house prices and includes both numerical and categorical features. The dataset contains 2000 price rows and 12 columns. And now pre-processing. Pre-processing is a critical step in preparing raw data for machine learning models, and it ensures that the data is clean, consistent, and ready for training. The pre-processing step includes handling the missing data. We have found out missing values in our data, which includes 91 in basement F and F2 column and 61 in total basement SF column. We have used k nearest neighbors, which is KNN imputation, to fill in those values. KNN works by looking at the nearest rows based on the feature similarity to estimate the missing values. And coming to the outlier detection and removal, outliers are extreme values that differ significantly from the rest of the data. This could be houses with extremely high prices, usually larger lot sizes, or properties with abnormal features. We have found no outliers in our dataset. And the next step is feature encoding. Our dataset contains categorical variables like MS zoning, which is type of zoning, and the building type. We have applied one-hot encoding to convert categorical variables into binary columns. One-hot encoding creates a new column for each category within a feature and assigns a value of 1 if the feature belongs to that category, or otherwise it assigns a 0. And coming to the feature scaling, our datasets includes features with different ranges and units. So machine learning models can give importance to features with larger scales, which could lead to biased results. So we have applied standardization to numerical features. So standardization transforms the data in a way that each feature has a mean of 0 and a standard deviation of 1. If you look at the formula to calculate the standardization, where x stands for the original value and the nu is for the mean and the sigma is the standard deviation. And the next section is proposed work. We have explored multiple regression models and selected the best performing ones for us and applied them to the pre-processed data. In this section, we will walk through the machine learning models that we have proposed and used, and why we choose them and how they work. And here are the selected machine learning models. The first one is ridge regression, and the second one is decision tree regressor, and the third one random forest regressor. The first algorithm that we have used is ridge regression. Ridge regression is a type of linear regression that includes a regularization term to prevent overfitting and improve the generalization of the model. In traditional linear regression, the goal is to find the best fitting line by minimizing the sum of square errors. However, when features are highly correlated or when there are many features, linear regression can become overly complex and overfit the data. Ridge regression addresses this by adding a penalty term to the loss function, which discourages the model from fitting to small fluctuations or noise in the training data. Here is the cost function that we have used to calculate. When we look at the formula, y of I is the actual price and y cap I is the predicted price. Theta of j is the coefficient of the jth feature. And most important, lambda is the regularization parameter which controls the strength of penalty. And addition of this is key difference between ridge and a normal linear regression. Why we have chosen ridge regression? We have chosen ridge regression for this project because there are some features that may be highly correlated. For example, large area and grid area may have similar pattern, making it difficult for linear regression to estimate the cost. Ridge regression adds a regularization term that reduces the effect of correlated features, ensuring that model remains stable and generalize better. Ridge regression helps to avoid overfitting by limiting the model's complexity. By shrinking these coefficients of less important features, it forces the model to focus on the most significant relationships in the data. Regularization helps improve the model's performance of or on unseen data, which is crucial when predicting house prices for new or future properties. And now let us see some key features which has large impacts. The first one is lot area. Larger lot area is generally correlated with high house prices. Ridge regression helps to quantify this relationship while avoiding overfitting to noise in the data. And the next one is overall quality. The overall quality of the house is a significant predictor of its price. Higher quality houses generally command higher prices, and ridge helps capture the relationship without overemphasizing less important features. And the next one is year built. Newer homes tend to have higher prices, and ridge regression helps model this linear relationship while preventing any extreme coefficients from skewing predictions. And here's the model performance of our ridge regression. After training the ridge regression model on our housing data, we have measured its performance and obtained the below output. And the training time it took is 0.002 seconds, and the R squared that we have obtained is 0.6958, and the RMSE value of 44732.03. And here are the metrics of model performance on our ridge regression algorithm. The training time that this algorithm took is 0.0020 seconds, and the root mean square error value is 44,732.52, and the R square that we have obtained is 0.7020. This R square value indicates that the model explains 70% of the variance in the house prices.
Hello everyone. Today I'll be discussing about two most powerful regression methods, which are the decision tree regressor and the random forest regressor. We will delve into their conceptual overviews, implementation details, their performance considerations, insights from a comparative analysis, particularly for the tasks like house price prediction. Coming to the overview of these algorithms, the decision tree regressor is basically a predictive model that splits the data recursively based on the feature values. It makes predictions by averaging the target values in the leaf nodes. While coming to the random forest regressor is basically an ensemble model composed of multiple decision trees. Each tree is basically trained on a random subset of data, and the predictions are averaged to enhance accuracy and reduce the overfitting. The main objective of the house price prediction system to use these both models from scratch is to gain a deeper understanding of decision trees mechanics and the ensemble modeling, especially their impact on regression tasks such as house price prediction. Now, let's understand the conceptual overview of a decision tree regressor, how the model works, and what are the important things we should keep in mind while building a decision tree regressor. The main goal of this decision tree regressor is to predict the continuous values like the house prices by recursively splitting the dataset based on the features to minimize the error. The structure of decision tree composed of two main things. One is nodes and the leaves. The nodes are basically the decision points based on the best feature, and the leaves are the targeted value. Typically, the target value are saved in the leaf nodes. The splitting criteria is one of the most important thing we have to consider when building a decision tree regressor. The splitting criteria is basically when the tree splits the data at each node based on the feature that minimizes the mean square error. Let's now look at the decision tree regressor in more detail, specifically how we build the tree and key steps involved in the fitting and prediction process. For building a decision tree, the three important steps are initialization, fitting the tree, and the prediction. So we begin by setting parameters like maximum depth, which controls the depth of the tree. Limiting the depth prevents overfitting, like a deep tree memorizes trained data too closely, while the shallow one might underfit. Fitting the tree. The tree is built by recursively splitting data based on the features that minimizes the mean square error. At each step, the best features and the thresholds are selected to create a homogeneous group of target values. The process continues until the tree reaches the maximum depth or all the nodes are homogeneous. Coming to the prediction, once the tree is built, predictions are made by following the path from root to leaf. The leaf node stores the predicted value, typically the mean of the target values in the node. For example, for the house price prediction, the leaf would have stored in the average house price of the data points reaching it. Coming to the key insights of the decision tree model for house price prediction, the decision tree regressor showed a high variance on testing data, indicating overfitting, but it performed well on training data but struggled to generalize. Overfitting occurs because a deep tree memorizes the training data, including noise rather than the learning the patterns. Pruning for this prediction, like limiting the depth tree, helps improve a generalization and reduce overfitting. This decision tree regressor has been evaluated on two different matrices. One is RMSE and the R-score value. The RMSE is basically the error metric for the model. For our model, it is 38,268.01, which quantifies the average magnitude of the prediction errors. Coming to the R score of the house price prediction model, the model's coefficient of determination is 0.774, meaning the model explains about the 77.474% of the variance in the target variable. The training time of this model is 0.162 seconds. Now we'll be discussing about the random forest regressor and its concept. The goal is to improve the accuracy and the robustness by combining the predictions from multiple decision trees. Basically, random forest is an ensemble learning and is a collection of decision trees. Each tree is basically trained on a random subset of data and features. The final prediction is averaged across all the trees. The key idea is by averaging the predictions from multiple models, and this random forest model reduces overfitting and provides a better generalization on the unseen data. Now let's look at the random forest regressor and its key steps. It also follows a three-step, the initialization, bootstrapping, sampling, and the prediction. In the initialization process begins by setting parameters. One is the n estimators. This defines how many decision trees will be included in the forest. Maximum depth. This is same as decision tree. This controls how deep each individual tree can grow, helping manage complexity and overfitting. For training the model, Random Forest employs two different strategies to ensure the diversity among the trees. One is bootstrap sampling and the random feature selection. Bootstrap sampling is in each tree is trained on a random subset of data selected with replacement. This introduces a variations in the trained data for each tree. Random feature selection. In this one, at every split, only a random subset of features is considered. This prevents all trees from focusing on the same features, improving the model's generalization. Coming to the prediction part, once training is complete, each tree in the forest makes a prediction. And the final prediction is calculated by averaging all the individual tree predictions, which stabilizes the model and reduces the variance. The key insights of random forest regressor for house price prediction. It consists of two different things. One is bias variance trade-off. The random forest achieves a good balance by averaging predictions, reducing overfitting compared to a single tree while maintaining the accuracy. Coming to the training time of this increases because the training multiple trees increases computational cost, but the improvement in accuracy justifies the additional cost. Coming to the evaluation of the random forest regressor, it has been evaluated on two different parameters. One is RMSE and the R-square value. The RMSE of this model is the 36,069.55, which measures the average magnitude of the prediction error, which is better fit than the rich and the decision tree models, which we have earlier stated. The R square of this model is 0.8022, meaning the model explains 80.22% of the variance in the target variable. Coming to the training time of this model, as I've already mentioned, the computational cost, it has taken 12.4636 seconds, showing the computational time required to train the model is high.
Now moving on to hypothesis testing, we have conducted a paid t-test hypothesis testing, and you can just view the results of the hypothesis testing right here. With the alpha value of 0.05, we did not see a lot of significant difference between any of the two compared models, that is like random forest decision tree and random forest versus ridge and decision tree versus ridge. So on the basis of mean MSE, we have concluded that the random forest is the best model. The three metrics that we have used to measure the performance are RMSE and R square and MSE. RMSE measures the average difference between the predicted and the actual house prices. Now a lower RMSE means that the model performs better. So in our case, we can see the different RMSE values, and out of all three models, the random forest got the lowest RMSE value. So according to the RMSE, it is our best model. Coming to R square, which tells us how well the model explains and the variation in house prices. Usually the higher R square is better and indicates the model fit. So again, in this case, we got highest in the random forest model. So it is the best fit out of the three models. And again, a lower MSE is better. And then we, from out of the three models, we can conclude that random forest got the lowest RMSE value, sorry, MSE value. So again, the random forest is the best model here. So to wrap things up, our project was all about creating a system that can predict house prices. We tested a variety of models for this purpose, and we have used ridge regression, decision trees, and random forests as discussed in the previous slides. We found that random forest gave us the best results. It has the highest R square value and also has the lowest RMSE value. But it wasn't just about getting the best predictions. We also wanted to make the system useful and transparent for users. So we included features like real-time price predictions and visualizations of feature importance, which will be demonstrated in the demo. What that means is when someone inputs the details of a house, the system doesn't just give them a price, it shows them which factors affect the price and how the models are performing and what models they can select to use prediction. Looking ahead, there's still a lot we can do to make the system even better. Uh, First, we can expand the database. Right now, our system is based on a specific data set, and we have included it in the web application that we made. To make it even more useful, we want to expand it by including more regions and types of properties. This will help the model make better predictions for houses in different areas. Another thing that we can have future work is adding more advanced models. We also want to try more advanced machine learning models like gradient boosting or XGBoost. These models have a reputation for handling more complex patterns in the data and could push our prediction accuracy even higher. Another feature we would love to add is ability to track and explore price trends over time. Imagine uh, being able to see how house prices have been changing in a particular area. This could provide users with deeper insights into the market and help them make even more informed decisions. Uh, Another thing we can work is on user interface. For now, we have a basic user interface, which I'll show you in the demo, and you can really make the app a little bit better. Now let's move on to the demo part. Now, this is the demo of our project, and this is the web application that we have built to predict house price. Uh, this is the home page of it, and when you click on prediction analysis, it takes us to the model performances page. And if you do predict, and this takes us to the actual prediction page that where you can give the input values and get a price out of it. And furthermore, you can just directly go to those pages directly from clicking on this tab. And this is the data table, and this is just the data that we have used to train these models. And you can just download the data from here. And you can also view model performance dashboard. So let's go to the model performances. Let's see a ridge regression. This shows how our models are performing, actual versus predicted plot and residual plot. And we can see these plots for the various models that we have used. Now let's just do a simple prediction right now. Let's enter 75, MS zoning classification. Let's say all, enter number. Let's say lot, it's a big house, 656,800. Lot configuration, let's say corner. Building type, let's say duplex. And overall condition of the house, let's say it's in a really good condition. And built 2003, let's say year remodel 2008. Exterior color of the house, let's go with the cement. Basement finish type, let's say 250. And basement in SF, let's say 1500. Bedrooms, let's say it's 4 bedroom house and 3 bath. And let's say we are using a random forest. Let's do this predict. So here we can see time taken to for the prediction to be happening and the predicted price. We can go here and see the model performances. It's going to take a little bit of time, and see, this is the model performances. You can see it in various plots, so you can get better understanding of these plots. And you can do this for all the models as well. that's all about the demo.